In the previous video, what we did was define what a well ordering is, among other things, and we gave some examples of well orderings. What we're going to do in this video is we're going to prove some useful characterization of what it means or when it occurs that a set is well ordered. So namely, a set is going to be well ordered if and only if there's no infinite descending sequences. So before we do that, what we need to give first is a definition of a sequence. Sequence, sometimes you might write it like this, xn with in between some brackets. What is a sequence on A? So on some set A. Well, what is it formally? It's just a function from the natural numbers into our set A. Just a function, say f, from omega into our set A. And as an abbreviation, kind of formally this is an abbreviation, but we'd write maybe x of n instead of f of n. Instead of f of n. That's what a sequence is. What is going to be our characterization for being well ordered? I'll erase this first and then. So what's the lemma? The lemma is that suppose that A less than is a strict linear order. Well, then A less than is going to be a well ordering if and only if there's no infinite descending sequences. So then A less than is a well ordering if and only if there are no infinite descending sequences. There are no infinite descending sequences. And to be more formal about that, what we mean when we write there are no infinite descending sequences, what we mean is that there isn't a function there's no function f there's no function f from omega into A, so that, well, if you're further along in your list in our sequence, then you're smaller than the previous thing, so that for each n and m, well, if n is bigger than or equal to m, then f of n is less than or equal to is less than f of m. So this is what I mean when I say an infinite descending sequence. How do we prove this? One of the directions actually uses the axiom of choice. But let's not do that direction first. So how does the proof go? Let's do this direction first, the right direction. Assume that we have a well ordering. We want to show that if something's a well ordering, then there's no infinite descending sequences. What we'll do instead is we'll do the contrapositive of that. So assume that there is an infinite descending sequence. So assume that xn is an infinite descending sequence. And what's the trick in this direction? Well, what does it mean to be well ordering? It means that all of your non-empty subsets have a least element. So let's just maybe follow our nose a little bit, and let's consider the set of all of these elements xn. So consider the set S, which is the set of all xn, so that n is in omega. So the sequence cared about the order, but the set S doesn't care about the order anymore. Well, this thing is non-empty, right? Because this is a function. We're listing out infinitely many elements in our set A. S is non-empty. And what does it mean for A to be a well ordering? Because S is non-empty, S has to have a least element. So S must have a least element. Well, let's call that thing, how do we want to write this? So S must have a least element, say Y. Say Y. Y is the least element of S. Well, by definition, what has to happen? If Y is the least element of S, Y has to be equal to xn for some n. So Y is equal to xn for some n in omega. But why is this a contradiction? Well, our sequence we've assumed is descending. But then xn plus 1, by definition of what it means to be descending, that has to be less than xn, but that's equal to y. Since xn plus 1 is also in our set, we reach a contradiction. Reach a contradiction. That's this direction. If there was an infinite descending sequence, that if we consider the set of all of those points, that couldn't have had a least element. What about the other direction? Get a little bit more space. So we need to show now that if there's no infinite descending sequences, then our set A was well ordered. And what we'll do instead is also just do the contrapositive of that statement. So we'll show that if A was not well ordered, so we're going in this direction now, we'll show that if A was not well ordered, not a well ordering, well, then there was an infinite descending sequence. Okay, so how do we do this? Well, by the definition of what it means to be a well ordering, if A is not a well ordering, what must happen is there's some set S without a least element. So by definition, there is some set S, the subset of A, that is non-empty and it doesn't have a least element. So intuitively, what's about to happen here is we're going to, since it's not empty, it's going to have some element. S is going to have, say, we know it has some element X. And, well, because S doesn't have a least element, what has to happen is there has to be some, maybe be suggestive, we'll call this thing X0. And because S doesn't have a least element, there has to be some element less than x0. So there has to be some element that's less than x0. That's also an S. But then we apply the same logic again. Because S doesn't have a least element, there has to be some element less than x1. It's called x2. And then there has to be some element less than x2. And we keep on going on like that. So how do we make this a little bit more formal? We're technically using the axiom of choice when we do this. Or at least a form of the axiom of choice. So how are we going to make this a little bit more formal? Well, for each set y in S, what we're going to define is kind of the set S sub y. And what's S sub y going to be? It's going to be a set of all x in S that are strictly less than y. Now, the point is that for each y in S, because S doesn't have a least element, Sy is non-empty for each y. So note that S sub y is non-empty for each y. So this is helpful for us because now, by the axiom of choice, what we'll be able to do is we know that there's going to be a function that's choosing an element out of all of these sets. So by choice, there's a function. And this function is going to be from S into S. So that what's true? So that for each element of S, for each y in S, well, f of y is going to be an element of S sub y. And if we just kind of write out what this means, is this is just another way of writing, we're just choosing an element that's less than y. So f of y is less than y. That's all we did there. Then what we can do, what's going to be our sequence? It's going to be a recursively defined sequence. So define. So recursively, we're going to define the sequence xn as follows. Well, we can pick anything for the first element in our sequence. So we're going to choose x0 to be arbitrary. It could be any, or maybe pick your favorite x0. Choose your favorite x0. And then recursively, how do we define the next element of our sequence? We're going to apply our function f to that previous element. So given xn, so maybe assuming that we've defined xn, we've defined set xn plus 1 to be equal to f of xn. And the observation that's important for us is that this thing is going to be strictly less than xn, right? By choice of what our function is doing. Well, this sequence is going to be an infinite descending sequence, and then we win. The sequence is descending. But that's exactly what we wanted to show. We showed that if our set wasn't well ordered, then there was an infinite descending sequence. Okay, so what we're going to do next is we know that we can say do things recursively for the natural numbers. We can prove things by induction on the natural numbers. But one of the nice things about well orderings is that we can also define things recursively on well-ordered sets. And we can also do things by induction on well-ordered sets. And so what we're going to do next is prove that we can, for well-ordered sets, do proofs by induction and also give recursive definitions.